Okay, so welcome back for the second part of chapter 2. We've gone through our basics on increasing internal energy. We'll look at the difference between a state function and a path function. You may have heard of this before, you may not have. It's a new thing. Sit back and relax. Get ready for it. So we've seen state variables P, V, and T, and we've seen the state function U. Well, notice how all of these are given as an uppercase letter. These state functions, special value. Now, these path functions, W and Q, have a lowercase. The big difference and why this is important is that state function will only depend on the initial and the final state when you calculate them. So it does not matter how you go about calculating the internal energy, because if I take 5 different steps before I end, so I change that, go over there, change that, go over there, and then there, or if I go one step or go this crazy route, it doesn't matter. A state function says that will be the same. Path functions will change. So the idea being that if I do reaction one way, I might have more heat. If I do it another way, I might have more work. But the change in internal energy will be the same regardless. The idea that internal energy is just a function, the integral of the change in U. So you have UF minus UI, final internal energy minus the initial internal energy. If you do it in one big step, 50 little steps, you get the exact same number. This is an exact differential, so we can know the exact value of this. That's so sacrosanct is that a cyclic path, which state function is always 0. A cyclic path is if you go from the final step to the initial step and back to the final step, you go back to the initial start, you get 0 change. So U final minus U final is 0, U initial minus U initial is 0. Well, if I did this as a path function, I went all the way over here with the heat and the work, and I took a different path back, the heat and the work will not have gone back to 0. This will be true for all state variables as well. The path functions will not be 0. And we'll explore that more later in several problems. It'll be tedious, but it can be done. You just have to look at ideal gas equation and what we know. Equilibrium will be a big thing in that we can only apply thermodynamics to systems in internal equilibrium, being defined as overall rate and change of all processes is 0. So how can we deal with heat, work, and internal energy? We'll break down this big process down into something smaller that we can look at. Change is so small, so gradual that diffusion and intermolecular collisions will happen on a much faster time scale. So all these small changes will create a quasi-static process. Make changes so small that it looks like there's no change at all. With that in mind, we can consider this 2 situations: reversible and irreversible processes. In a reversible process, an infinitesimal change could reverse the process. Small steps can get it back. So, like, for example, we have 2 balanced weights. I add a grain of sand to one side. It's now out of balance. If I remove that grain of sand, it gets it back in balance. But an irreversible process, we could not undo this. Like, say if you have equal amounts of sand and perhaps ice cubes. As I allow the ice cubes to melt and run off of the balance, it's going to be a lot harder to get them the system back in balance. Oftentimes, very large changes will result in irreversible process, something where you can't put this back without inserting extra energy into the system, like allowing a gas to expand into a vacuum. In order to push it back, you have to apply work to reestablish this vacuum. So here's where we get looking at path functions and a reversible and irreversible process. So path functions are dependent on how we calculate this. So we got to think about this in terms of our ideal gas equation. So irreversible expansion of a gas from V1 to V2 under external pressure, and then V2 to V1 under a new pressure will result in two paths not being equal. So even though the delta V will be equal and opposite, the P, the pressures, will not be equal and opposite. So if I add the work from step 1 to the work to step 2, they do not cancel out. So if I have a 5-gram weight, I allow the gas to expand under the 5 grams of internal pressure to get it back to the original state, I will have to put a heavier weight on there. So I have a greater external pressure. If we would break down to this into infinitely smaller steps, we could eventually approach work equals 0, so long as the change is irreversible, the path will matter. A reversible change is we'll get infinitely small steps, so that work total will essentially equal 0, and we could get it back. Now, in order to calculate this for infinitely small changing P and changing V, we'll have to calculate this as an isothermal process. So isothermal meaning PV equals nRT, and T is held constant. So if nRT is constant and P is not, we are going to exchange P for nRT, replace it with nRT. So that so essentially we have remember our work is P delta V. Well, P is changing, so we cannot include P in there because we're not looking at delta P as well. So we're going to exchange this where P is equal to nRT over V. Now, we still multiply that by delta V. So when we integrate this, nR and T factor out because they are constant. But V is our variable we're going to integrate them with respect to. So 1 over V dV, when we integrate that, that becomes ln of V, F minus ln of Vi, or ln Vf over Vi. So to look at a reversible isothermal process, where we allow temperature to stay constant throughout, we look at the work of this system is negative nRT ln Vf over Vi. This equation will give us the exact same path forward and the exact same path back, allowing work total to equal 0. Now, essentially, if I did this in 2 big steps, 2 small steps, we're going to irreversible expansion and compression, we're going to lose some of that energy. But if I do it reversible, I can get a perfect integral. In order for the temperature to stay constant with changing pressure, an external temperature sink must be available in order to transfer heat in. So as this work is being done, heat must flow in to keep the temperature constant. So in this, to keep our delta T 0 means Q in will equal negative work out. So whatever our work isotherm is, it's equal to negative Q. that in mind, delta U, which would be Q plus W, would have to then be 0. Because if Q equals negative W, Q plus W would cancel out. So an isothermal system would have no internal energy change for this reversible situation. So let's calculate the work of isothermal expansion of a gas from 15 bars to 2 liters under external pressure of 1 bar. So first calculate this as a reversible process, a reversible 1-step process, and a reversible 2-step process where we go 1 to 2. As a gas, 15 bars. So it's currently at 15 bars. And he's going. So first step, this is going to be a repetitive step that's going to be annoying as all hell, but it can be done. And that isothermal expansion, we don't have a lot of variables we need, but it all comes back to PV equals nRT. The first situation, we don't care about nR, but we do care about T, or at least nRT. We're given it's 15 and 2, so nRT is going to be 30 for that first situation. Now, second situation, it's going to have expanded until it's at 1 bar external pressure. 1 bar. One bar external pressure. So now, if it's equal to 30, our volume at situation 2 must also be 30. So right now we have nRT equals 30, and we have V2 is going to be equal to 30 liters. Now, I'm going to erase some stuff. So let's calculate this first for what I'm going to do. The irreversible. Well, we'll do the reversible process. So we have work of an isothermal reversible process, negative nRT, so negative 30. Still have to multiply by 100 to get that into joules over VF minus VI. VF, ln, VF over VI, ln 30 over ln 2. So 30 times 100 times ln 15. So we have 8124 joules. So that's how much work can be done in a reversible process where you have infinite steps. Now, if I did this under a reversible process, work of 1-step work is equal to negative 1 bar times our change goes from 30 to 2. 30 minus 2, and we times by 100 to get this into joules. So 28 times 100, so, well, we lost a crap ton, so 2800 joules. That sucks. Well, 2 steps. Well, we got to do this PV equals nRT again. So we have to say V V3 is still 30 in this case. V3 is 30, but now V1 is still 2. But now V2 is somewhere in the middle. V2 is 30 equals 8 times V2. 30 divided by 8, you have 3.75. Okay, so you add the two steps together. So work, step 1 is negative 8 times 3.75 minus 2. 1.75 times 100. So that's a negative 1,400. And then the step 2 is negative 1 bar. And we're going from 3.75 to 30. So 26.25 times 100. So 2625. So we look at this, 2625. This two-step process gave us negative 4,025. So two-step process gave us more work than the one-step process, but still less work than the reversible process. So as you increase the number of steps, you can generate more work out of this process, but we're still always going to be less than a reversible process. Less than. So, but either way, the idea is we can calculate the constants using the ideal gas equation each time. So we're going to introduce enthalpy, a new constant. So remember that internal energy, U equals Q plus W. And this is real simple when volume is constant. Because when volume is constant, work is 0. So we can state absolutely and definitively, and this will come up so often it will make your head spin. But an isochoric process, when volume does not change, internal energy change is always equal to the heat flow at constant volume. Because this is a state function, it doesn't matter what situation this is going on, we can always say that internal energy would be the energy change if we calculated the heat flow at a constant volume, even if volume is changing. If we can calculate it from QB, we can calculate internal energy rather than do it the hard way. So, well, what happens when we calculate the heat flow under constant pressure conditions? So we still say in changing U is equal to the changing Q minus P dV. Integrate this. Integrate this. We're going to get, so UF minus UI equals QP. And then we're going to have negative P VF minus VI. But if we allow this to do properly, we can say that is equal to QP minus PF VF plus PI VI. Getting those to the other side, knowing that PF is equal to PI, say that UF plus PF VF minus UI plus PI VI is equal to QP. Equal to QP. Saying QP is equal to change in internal energy plus the change in work, plus work, essentially negative work, or plus pressure change in volume. Now this QP is equal to our state function. So we've defined this path function, Q, in terms of a state function, which doesn't matter the path. We're making this very specific path function as just the path of a constant pressure heat. And that gives us the state function H, because it's all in terms of state variables rather than a path variable. That is our enthalpy. That's our really helpful, where the enthalpy is the potential for heat flow under a constant pressure. Now, while this is similar to Q, it is not exactly identical to Q. That's one thing. And H is a state function and will vary in relation to Q depending on the situation. But we can always say Q sub P is equal to enthalpy. Now, there's some implications here that since ideal gases are functions of state variables at a constant pressure, U is a function only of V and T, because pressure is no longer available. Since ideal gases do not interact with each other, it said that we no longer a function of volume, so that internal energy can be just a function of heat flow. Thus, we can calculate internal energy for CV delta T, even when pressure is constant, because once again, the nature of the state function. We can say the same for enthalpy, so we can always calculate enthalpy as QP, which is CP delta T. Next problem, example problem, will prove this and show the difference between a path function and a state function. So this is a cyclic path. Step 1 mole of ideal gas will expand at a constant pressure of 20 bars from 1 liter to 16 liters. Constant pressure expansion. Gas will cool at a constant volume to a pressure of 1.25 bars and then go isothermal compression back to the original volume. I give you the C sub P. What is the Q, W, delta H, and U for each step, and what is it for the whole cycle? So we're going to do it step by step by step. The first thing we want to do is calculate if this is step 1, that's 2, that's 3. P1, P2, P3, V1, V2, V3, T1, T2, T3. So 20 bars, 20, 20, 1.25, 1, 16, 16, and we're not given the temperature, but we're told, well, I've told you that it's 1 mole of ideal gas. So in situation 1 times 20, 1 liter times 20 divided by 1 mole divided by 0.08314. So we'll say 240.6. 40.6. Let's do that again. 20 times 16 divided by 0.08314. It's going to be a bigger number. 38, or I say 3849. Good Lord. Ah. Oh, come on. Right over to 3849. And because 25 of the isothermal, we should probably expect the last one to be 240.6 as well. 240.6. So there's one more value we need before we want, and that's C sub V. C sub V. C sub V, remember, C sub P minus C sub V equals R. So 35.7 minus C sub V equals 8.314. That means C sub V is 35.7 minus 8.314. C sub V sub M is 27.386. Okay, we have everything we need to go forward. So I'm going to prove this to you the easy way or the hard way. On each step. So we'll start with this. So the first step, constant external pressure, it expands from 1 liter to 16 liters. So expansion of 15 liters at an external pressure of 20. So we have a change in 300 times 100. So I'm gonna, so it's negative 30 kilojoules. Negative 30 kilojoules. Now, this is a constant pressure system. Constant pressure system. So C sub P is 35.7. It's gone from, and we multiply that by 3849 minus 240.6. And we divide by 1,000, get that into kilojoules. So we get 128.8. Okay. So C sub P, or Q sub P, is going to be 128.8. But if I add heat plus work, I should get U, which is going to be 98.8. Now, let's hypothetically calculate that with C sub V. 27.386 times our change of 3849 minus 240.6. What do I get? Divided by 1,000, I get 98.8. I get the same value doing a shorter step than I did when having to add Q plus W. I get the same value. Step two. Step two is our volume stays the same, pressure changes. So PV, P delta V, so this is 0. Our heat, since it's a constant volume, is just Q sub V. Q sub V, so 38, so we have 27.386 times, we have 240.6 minus 3849. So, surprise, surprise, we get negative 98.8. That's going to be negative 98.8. Now this guy is going to be, we can calculate as C sub P. Let's see. C sub P. So C sub P, that's going to be negative 128.8. There's a reason for this. Now, finally, here's the big thing, the isothermal step. Remember, isothermal, Q, negative Q equals W equals negative nRT ln VF over VI. So, at 8.314 times 240.6 divided by 1,000 times ln, we're going from 6, the VF would be ln1 divided by 16. And it's negative here, so this is going to work. It's going to be positive 5.56, and this is going to be negative 5.56. Add this together, there's going to be 0. But because the temperature does not change, 240 to 240, C sub B will make this 0. 240 to 240, C sub P would make this 0. I add up negative 128.8 to positive 128.8 plus 0 gives 0. Positive 98.8, negative 98.8 plus 0, 0. You get 0 internal energy change in a cyclic process. We get 5.546 minus 30, negative 24.5 work on the cyclic process, 128.8 minus 98.8 minus 5.546. You get positive 24.5. So for this whole cyclic process, what we see in this path-dependent functions, we see internal change in heat of positive 24.5. Negative 24.5 kilojoules of work are produced. Thus, you see work produced so long as heat is being introduced. And so even though the internal energy stays the same. I may have goofed on the sign somewhere. It's not super important. The important thing is that either way, they're not equal. Just a second. So the last situation is dealing with an adiabatic expansion. So isothermal, we can deal with. Isochoric, isobaric, we can deal with. Adiabatic, where heat is not allowed to change. That means there has to be some temperature transfer from the surrounding system to surroundings. So that means both pressure, volume, and temperature will change, yet Q will equal 0. So we can solve for this knowing that pressure, volume, and temperature in any given situation. So I'm going to jump to a proof real quick to get how we get here. So knowing that Q equals 0 and internal energy will have to be just our work. So just equal to negative P delta V. But we also know that no matter what, even though this is stupid, even though we know heat flow is zero, internal energy also equals C sub V delta T. Now we're going to get rid of the pressure variable, because once again, the pressure variable is changing. So rather than dealing with 3 variables, we're going to get this in terms of 2. So pressure equals nRT over V. So we can get this equal to negative nRT over V dV C sub V dt. If we get the temperature to the other side, we get negative nR V dV equals C sub V over T dt. All well and good so far. We're going to integrate this with respect to our variables to get negative nR ln VF VI equals C sub V ln TF TI. Now here's where it gets a little tricky. Here's where it gets a little tricky. If nR is equal to C sub P minus C sub B, we can exchange the negative nR for C sub P. So it becomes C sub V minus C sub P. So that's what we're exchanging for. And because of the negative sign, ln VF over VI equals C sub V ln TF over TI. And then dividing by C sub V, we get this to be 1 minus C sub P over C sub V ln VF over VI ln TF over TI. And they often abbreviate then in turn C sub P over C sub V, because those are both constants. We exchange it for variable gamma. So 1 minus gamma ln VF over VI equals ln TF over TI. So that becomes gamma. Now, if we use the rule of logs and take inverse log to both sides, you can get this as TF over TI equals VF over VI 1 minus gamma. Because these are constants, you can find a real value for gamma and plug this in. What this allows us to do, is to find an unknown volume if you know 2 temperatures, or one volume and 2 temperatures. Or it allows us to find a second temperature if we know both volumes and one of the temperatures. Now, one more thing. We can also exchange this. We can say that TF is equal to PF PI or VF. And so our equation down there becomes PF VF over PI VI. And taking the logical expansion of 1 minus gamma, the other side, we get VF over VF gamma, because a negative makes it an inverse, times VI on the bottom, VI gamma. Now, exchanging this over, these start to cancel out, and you get PF VF gamma equals PI VI gamma. So that's one version. There's another version, essentially allowing us, under this crazy adiabatic equation, to calculate one of our ideal gas variables when we can't possibly know it any other way. That's what this will allow for us to do. Okay. So now, so if a heating occurs under adiabatic compression and cooling under adiabatic expansion, we'll see it in action. So this is the last slide of this. So 1 mole of smoke coming out of factory chimney at 500 Kelvin is about 0.946 atmospheres. The smoke will undergo reversible adiabatic expansion into the atmosphere, and the smoke cools to 230 Kelvin in the upper troposphere. What pressure of smoke if the C sub P is equal to that? So first things first, we need our VI before we go any further. But they're like, oh no, we don't have it. But we have our ideal gas equation. We will always have our ideal gas equation of PV equals nRT, VI, 1 mole of smoke. Doesn't matter what smoke is. No, it's an ideal gas. So 0.08314. Oh, I gave you this in bar. So 8206 times 500 divided by 0.946. VI is 43.37 liters. Okay. So we know our second temperature. Next thing we need is C sub P. Like, oh no, we don't have C sub P, but we know that C sub P minus C sub P equals 8.314. 28.86 minus 8.314 gives us our C sub B, 20.546. And gamma is equal to C sub P sub M over C sub B sub M. So 28.86 divided by 20.546 is equal to, oopsies, 1.40, let's say 1.405. Probably good enough. Okay, so TF or TI VF over VI 1 minus 1.405. So 500 divided by, we'll say 230 divided by 500. You could do the natural log version. So I could take the natural log of that. I divide by 1 minus 1.406, 4.05. I get 1.917. Take the inverse log of that. Get 6.8, multiply by our volume, 43.37, and I get 295. So it is expanded to a volume of 295. Now we could use our expansion, adiabatic expansion equation to find the P2, PF, or we could just use our ideal gas equation and find the PF. It will give us the same value. So 290, so we're going to say 230 times 0.08206 divided by 295. Make sure I multiply the right number. Is the pressure of this in this upper troposphere is 0.063, well, 64. 0.64. Very, very low. But then again, it is the upper troposphere. So, kind of tricky, but there's no really other way to deal with that. And that is an example of adiabatic expansion. That is where I will leave you for today. So, thank you for joining. If it's semi-interesting, hopefully you learned something and enjoy the rest of your day. Please like, please subscribe.